In our past video, we looked at a simple supported beam with uniformly distributed load, and we were able to calculate the external forces, that is the reaction at AY equal to WL out of 2 and AX which is equal to 0. Then we also calculated for the reaction at the roller support B, which is BY is also equal to WL out of 2, and these forces are acting at a distance L out of 2 from WL, and this one also L out of 2 from WL. Then we also see that this is total force WL, which comes from the multiplication of the uniformly distributed load W, which is the width of this area, because this loading condition results into generation of a loading area, and the area of that graph gives us the total load in that particular loading condition. Therefore, it will be length times width, which will be width, which is W times L, and this gives us WL. And this total force WL acts at the center since it is a uniform beam, and it acts at a distance L out of 2 from A, the support. Now in this video we are going to look at how to use the information that we calculated for, that were the external forces and the internal forces. The internal forces included the bending moment and shear forces. Of course, we used the method of section, and we cut along any section at a distance x, and therefore we got the expressions that will tell us the variation of bending moment and shear forces as you move from one support to the other. Now, having considered of course, we used the method of sections, we cut, and we had the segment 1 and segment 2. Now let us take an example of segment 2. We know segment 2 was from where we had the section cut to the support B, and the reaction at B of course is WL out of 2, and is at a distance L minus X, since from the support A to where we created the section cut was at a distance X. So therefore we will create the bending moment in the opposite direction, which will be now clockwise direction. For segment 1, when you check in the past video, you will see that it will be facing in a counterclockwise direction, so that at the end of the day they cancel out each other. Likewise, shear force was facing vertically downwards, and now in this segment it should face vertically upwards to also cancel out that particular effect. Therefore, if it is at a span of L minus X and with a uniformly distributed load W, then to get the total load that will act at the center of this free body diagram of the loading condition L minus X, this W into L minus X will act at L minus X out of 2 from B, and also L minus X out of 2 from where we created a cut. Therefore, applying the equilibrium conditions to this free body diagram, sum of forces in the y direction or vertical direction should be equal to 0, since V, the shear force, is pointing in the positive x direction. WL out of 2, this reaction at B, is also pointing in the positive y direction. Then we take away this WL minus x, which is pointing vertically downwards, and this will be a negative. So if we solve this particular problem, we will find out that V L out of 2 minus W into L minus X is equal to 0. So V is equal to WL out of 2 minus WX, and this is as it was calculated for segment 1. Then the bending moments, of course, as we take moments about O, it will also give us the expression that we can use to calculate for the bending moments. And since M is in the clockwise direction, then it will be also having another clockwise moment, which will be W. Of course, this will be W minus X, okay, times L minus X out of 2, and this will be in a clockwise direction also. So that's why we are having this expression. It is W out of 2 into L minus X times L minus X. So if we square, you'll have X squared minus 2LX plus L squared. Then, of course, minus the counterclockwise moment as a result of this WL out of 2, which will remove, which will have a perpendicular, its line of action is at a perpendicular distance of L minus X from this point O where we are taking moment. Therefore, we shall have minus WL out of 2 into L minus X, and this is equal to 0. Then when I look at when I open my brackets here, I'll have M plus W out of 2x squared minus WLX plus WL squared out of 2 minus WL squared out of 2 plus WLX out of 2. So when I solve, finally I will have this expression, bending moment varying in this way as WLX out of 2 minus WX squared out of 2. I think this is understandable, and therefore we find out that we have the expressions for both shear force, and this is the shear force, the variation of shear force, and also the bending moments. Of course, all these expressions are the same for both segments. If you took segment 1, then you should be able to come up with the bending moment as this, and the shear force varying according to this formula. Now, if we bring the free body diagram with the expressions of AY, remember this AY is equal to WL out of 2. This BY is also equal to WL out of 2. Now, when we look at the expression for shear force, the shear forces, we will realize that it is a straight line that has got a negative slope. This is a straight line. Of course, it is varying in X. V is varying with the X, so it will have a negative slope, and therefore we have to know that the shear force at the support is AY, which is WL out of 2. So we will have WL out of 2 here, and we also, that is of course at X is equal to 0. If we put in our value as X equal to 0, that is at the support, we will find that this is W times 0, and we will have WL out of 2 as our shear force at that particular support. Likewise, if we put X equal to L, that is at the other support at the end, at this point X is equal to L. So if we substitute in L in the expression for shear force, we realize this will be WL out of 2 minus WL, and this will give you a negative shear force. So that negative shear force, you come and plot it here. It will be the same. It will be the same in magnitude as the first one here, but of course this will be negative. So I will find that since it is a straight line, I will just join these points. If I had a range of values from 0 to L, I can plot this graph, and it will be a straight line graph that has a negative gradient. So if we plot, we realize that at this point, at L out of 2, if we substitute in L out of 2 here, we find that the shear force reduces to 0. So if it reduces 0, of course that is true, and it will keep on now increasing in the negative direction as you also move away from this point. So by the time you move L out of 2 from this point, you will be having it in magnitude as W arrow out of 2, but of course with sign as negative W arrow out of 2. Now, if we are to also plot the bending moment diagram, we know at the supports we have this shear force moving a distance 0, so the bending moment will be 0, and also at the other support the bending moment will be 0. That is a must know. And we have also known that this loading condition has a maximum bending moment, which was already determined by substituting the value of x, where shear force is equal to 0, and we have it as W arrow squared out of 8. So bringing W arrow squared out of 8 as a maximum point here, we also know that this is going to be a curve. Of course, the shear force diagram, if it is a straight line with a negative gradient, we always find where there is a uniformly distributed load, it is going to be a curve. And since it is the path is parabolic, we know this parabola is always, since it is W arrow x out of 2 minus Wx squared out of 2, this is going to be opening towards the negative y direction. It opens towards the negative y direction. If I had the W arrow y out of 2 minus Wy squared out of 2, this would be opening in the negative x direction. So you need to understand the mathematics behind a parabola if you are to draw this diagram also. Therefore, the points will be equidistant from the axis, and therefore I will have those points plotted and join them, and this will be the bending moment diagram. Therefore, the important points here are where the shear force is equal to 0 is at x is equal to arrow out of 2, that is the center or the middle of the beam, and where the bending moment is maximum is where the shear force is equal to 0 and at a distance equal to x equal to arrow out of 2, and the maximum bending moment value in magnitude, of course, is equal to W arrow squared out of 8 Newton meter. Thank you so much for watching. See you in the next video.